Now in this section we'll be looking at the time of the kth arrival. So let's say that we're looking for the second arrival or the third arrival or the 10th arrival. We previously looked at the time of the first arrival, that is t sub 1, but now let's look a little bit further and say, can we generalize a formula that lets us know when the kth arrival occurs? And so to do that, let's just start out with a sequence, and we'll look at this sequence here where we have 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. And from here, there's a couple things that we want to look at. The first one is there a way to assign some random variables that will help us out? And the answer is yes. So let's first say that we have a y that is the time of the kth arrival, or the index of the kth arrival. So for this one, we would say that our y sub 1 occurs at this first one, and then we have a y sub 2 at the second one, and ultimately y sub 3 over here at this third one. So pretty straightforward. We've basically just assigned a random variable to the index, so y sub 1 equal 3 if you're starting from an index of 1, and then y2 equals 7, and y3 equals 12. Numbers don't really matter in this case, but just as an example. The other variable that might be useful is t sub I, where t sub I is the time that it takes from the previous arrival to the next arrival. And so we would say that this time right here is t sub 1, that this time here is t sub 2, and that this time right here is t sub 3. Now we do it this way because you can always add all of the t sub I minus 1s to t sub I to get the total time from when you start your process until you get the kth arrival. Now to put this in a little bit more formal definition, we say that y sub I is just the time of the kth arrival, and that y sub I would be equal ultimately to t sub 1 plus all of those t sub i's up to t sub k. So from here, we again can look at this. It's kind of what we just said, but if I want to know the time of y sub 2, that would be t1 plus t2. We also say that t sub k is the kth inter-arrival time, and inter-arrival time being the time from y sub k to y sub k minus 1, actually the time from y sub k minus 1 to y sub k. And it's the difference of those two. So again, this would be looking at the time from, say, y sub 2 and y sub 1. What is this inter-arrival time? Well, that is t2. Now, this only applies when k is greater than or equal to 2, because I have to have had a previous arrival for this formula to work. Now, one of the important things that we'll look at when it comes to a Bernoulli process, and also with a Poisson process, is that the process starts fresh. Go back to our lecture from MIT on the fresh start principle, that the process starts fresh after time t1. The process basically resets, and that's required due to independence. Now, to extend this further, let's look at the time of the kth arrival and use some of this information to help influence a generalized equation for the time of the kth arrival. So pulling from our previous slide, we said that y sub k is just equal to t sub 1 added together with all of the other t sub i's up to t sub k. Now, we also have determined from our previous lecture on the t sub 1, on the time of the first arrival, that t sub i's are geometric with parameter p. And we can say this because we have the fresh start principle, the fresh start property. And because of that, we know that t sub 1 was geometric earlier, but since we're resetting after each t, that t sub 2 is also geometric, t sub 3 is also geometric, and so on and so forth. So from this, we can say that the expected value of a given y sub k is just really the addition of 1 minus p for each t sub I that sums up to that y sub k. Now there's k t sub i's to get to the y sub k, as evidenced by this equation, right? It's t sub 1 all the way up to t sub k that we're adding together. And so from that, we can find that the expected value of y sub k is just k divided by p. Or another way to look at that is k multiplied by 1 over p. Now the next thing that we might ask is, what's the variance associated with y sub k? And the variance of y sub k is k times 1 minus p divided by p squared. Again, the 1 minus p divided by p squared coming from the definition of variance for a geometric random variable, and we're multiplying by k because we are interested in y sub k, which has k t sub i's added together. Now the next thing that we'll look at is just the PMF of this y sub k, and we can say that the PMF of y sub k with respect to our t, let's expand that out, right? And so the first thing that we would ask is, what's the probability that our y sub k is equal to a specific time slot t, or a specific time slot I, to use some of our previous lingo, but we'll mitigate, but we'll change that to t since t makes more sense for the time slot. In order to calculate this probability, we really need two key elements. And the first of that is that if we draw this out, we have some series of 0, 0, 1, 0, 0, 1 maybe. And so the first thing that we would ask is, in t minus 1 slots, there have been k minus 1 arrivals. So if this is slot t, this last one, and we're interested, let's just say, in y sub 2, then we would say that from the beginning to this slot right here, this last 0, that is t minus 1 slot, that there have been k minus 1 arrivals. And so in order for this to happen, we would say that there has to be, k in this case is 2, and so there must only be 1 arrival. And we see that because this was defined, there is indeed 1 arrival here, but what's the probability that there was only 1 arrival in this range? And then the second piece that we're concerned with is maybe the more obvious piece, and that is that there is actually an arrival, that there is a 1 or a success at the tth slot. So we would say that this must be a 1. And so what we're interested in is finding both of these probabilities. And then it's probably worth remembering that because this is a Bernoulli process, that the probability of each individual slot must be independent from that of all other slots. And so therefore we can just multiply these two probabilities together in order to get our total PMF of y sub k. Now, to look at this, we can go back to all of the same terms that we've used prior and all the same equations we've derived prior. We can say that in t minus 1 slots, there have been k minus 1 arrivals, and that would just be n choose k, where n, the number of slots, is t minus 1, and k minus 1 arrivals. I'm looking for k minus 1 arrivals in t minus 1 slots. Therefore, I'm doing t minus 1 choose k minus 1. And then I would multiply that by the probability of an arrival, p, raised to the k minus 1. And then multiply that by 1 minus p, the probability of a non-arrival, raised to the power of t minus k. Now, from here, the next question we would ask is, what's the probability of an arrival at slot t? Well, this is just a Bernoulli event, so we can say that that is really just p. that P is our probability of an arrival at slot T. So multiplying these together is what will ultimately give us this PMF of y sub k for a specific time T, or a specific slot T. So multiplying these equations, these two separate probabilities together, we find that the PMF of y sub k at T is just equal to the n choose k, t minus 1 choose k minus 1, multiplied by p to the k, multiplied by 1 minus p to the t minus k. Now, one of the things that's important to recognize here is that this is only for t greater than or equal to k. Now, to put that in different terms, we're saying that we have to have had at least k slots in order for this equation to hold. Up until we've had k slots, we can't have any probability of an arrival because we can't have, this equation's no longer valid. We've assumed that there have been k slots. So for all of these slots prior to this, we would have a probability of 0. So if we were to actually draw this out as a PMF of the variable y sub k, we would find that we really have a whole bunch of zeros here for all of these time slots, for these initial time slots. And then at some point, we're going to have an increase where we're going to increase to some maximum, and then after some point, it's going to decrease again and go on forever, really. So this is going to follow roughly a normal distribution curve, and we'll look at that in more detail later. But the probability all the way over here on the left is actually just 0. And the defining point here where we start to get a probability of arrival is that this is slot K. And so to make this graph look a little bit more like what it's supposed to, this would be K minus 1 down to 0. And so one of the other things that will be important is that, let's say I'm looking at y sub k being the 5th arrival, whereas this graph, let's say, is for k equal to 3, or the 3rd arrival. So one of the things that we can guess is that if we wanted to do k equal to 5, that this graph, this curve right here, would actually move to the right. That there is going to be the same type of curve, just shifted out to the right. And the reason for that is that there's more arrivals that need to occur. Now, the curve, depending on the probabilities, may compress or decompress, that is, expand or contract in width based on the actual probability associated with your geometric function, or more accurately with your Bernoulli random process, that probability P. But what you'll notice is that in general, it will take longer to get 5 arrivals than it will to get 3 arrivals, and that just makes sense intuitively. So that really concludes our discussion of the time of the kth arrival. We have a couple more topics to discuss in this lecture, but like I mentioned, there will be a quiz over this at the end, and then we will have some homework on this when we get back from spring break.